Thanks, everyone. Hopefully you are here to me to talk to you about managing asynchronous APIs. And by that I mean messaging systems, be they you using Kafka, RabbitMQ, whatever your poison. We'll talk a little bit about what happens when you succeed at event-driven architectures, and you now have lots of events and messages flying around your system, and you need to know how to manage that particular process. This just says I'm old, effectively. I think the point on the bottom one is the only one I'd like to call out, right? It's very easy to see this as kind of expert learner. I'm really just like you. I just got lucky enough to get into speaking and got reasonably confident about standing on a stage in front of you, but any of you could do this, and so I'm no smarter than you. Is it all Java people here, or do we have any .NET developers in the room hiding somewhere? Oh, we do have a few of you, okay. I work on a messaging stack for .NET called Brighter. For various reasons, you can find out if we wouldn't ever rug pull because our ownership structure works. So we will remain open source, and we therefore form an alternative to mass transit, et cetera, that are currently going closed source. All right. Let's talk about managing asynchronous APIs. In particular, we'll try and introduce an idea of 3 pillars that we need to think about. I won't tell you what they are yet because, a little bit of suspense. But let's talk about kind of how we get there. So one of the first things to understand is what we mean by an endpoint. So an endpoint is really just how does my application communicate with other things. And in particular, in our case, it's where are the messages sent that we receive in our application, right? So how do we send stuff? How do we receive stuff? That goes through an endpoint. And in particular, you can kind of define that as this kind of where, how, what. You can say what you need to know to understand an endpoint is where messages should be sent, how should they be sent, and what the message should look like. So we can draw a little diagram that kind of speaks to that. Now, I'm currently working with Just Eat Takeaway, so my example is going to be, including a restaurant. So imagine that we have a service called Restaurant Management. And that service called Restaurant Management wants to publish an event called Restaurant Hours Change. So maybe the restaurant owner has decided, I've had enough, I'm going to take a couple of days off next week and close the restaurant. So you can see we've got an endpoint where we're publishing this message, Restaurant Hours Change. Then there are a number of things we want to know about that particular message. Whoops, a daisy to me. So the first thing is, what is this message, right? So message is really just 2 things. It's metadata and payload, the body, right? So the metadata, usually headers, typically describe information about the message, often useful by people that don't want to process the message body, but may want to, for example, filter it or route it, or effectively in order to help you with the process of taking whatever is that payload and turning it into something you can use. Okay. And what we need to agree is what the metadata and the headers are, right? And we need to agree basically how we've encoded the body. So is it JSON, is it Avro, is it protobuf? In order to deserialize it, what does it look like? And we send messages over what we call a channel. Now, channel is really just messaging speak for either a queue or a stream. Queues and streams have slightly different semantics. So what we're going to do, I'm just going to get hold of something. I'm just going to plug in a clicker because it's going to be easier. Give me 2 seconds to do that. USB sticks never go in the first time, do they? Okay, all right. So a channel is really just a logical concept. It represents any kind of queue or stream that we want. It's named, it's unidirectional, right? So what we also probably do need to know, apart from the channel name we're sending stuff to, is what kind of channel we've got and how we talk to it. And that's really what binding is. So the binding is the details of the channel we implemented, basically what transport it is, say Kafka or AMQP, well, what effectively the encoding the message is, that kind of thing. And that's a lot to remember. There's a simple sort of system for remembering that, which is basically called the ABCs. The first time I ever saw this put down was a thing called Windows Communication Foundation on WCF for .NET. But basically, it is address. So the channel, where are we basically sending to or receiving from? The binding, what protocol are we using to send and receive? And the contract, what is the schema of the message that we are sending or receiving? And an endpoint effectively is an ABC. It's an address, a binding, and a contract. So we can begin to think about our messaging infrastructure as being a collection of endpoints that have addresses, bindings, and contracts. All right. If we are a small startup, and there are, I don't know, 24 of us in an office, or maybe even 24 of us virtually nowadays, generally speaking, if I want to understand what your endpoints are, I probably just walk over to your desk and ask you a question and you tell me. It's very simple. Or if we are remote, just get you on a quick call and we talk through it, and now I am much the wiser. And if we essentially need to understand how are the messages flowing in our application, then it's fairly easy for us to hover around a whiteboard or Miro and just sketch it out, right? And between us, we can quickly figure out, here are the messages that are being sent. And often it's pretty easy. If we want basically to get a Kafka topic, or we want to get, say, an AMQP exchange, it's pretty easy. It's just up to us, you know, or maybe there's one person in the team who we communicate with via ticket ops over Jira, and he does all that because, you know, maybe we should have some sort of security in our startup, right? Or even typically with with many messaging frameworks, for example, Brighter, the open source one I work on, typically we will provision for you. So if you declare what it is actually you're sending or receiving to, we typically have a flag and we'll say, great, we can go and check if that exists. If it doesn't exist, we'll actually make it. All right. And it's fairly straightforward to think about how we choreograph messages that flow around our system, because we've probably only got 24 of us. The number of communication points is quite small. When you get to scale, this begins to break down. Now, scale is, you know, your choice of at what point you can't communicate. I think even Dunbar numbers at 120 are likely to be excessive, basically, for what you could actually achieve. The first point is you just don't necessarily easily know who then owns an endpoint, right? Because you don't know who it is you'd actually have to ask in order to find out who the endpoint belongs to. You don't necessarily have any published contracts. So what is the schema of this message? Do I just inspect it from having a look at telemetry? Is there any telemetry? How do I know what shape it is? How do we know that the infrastructure that you've got documented in your repo is the infrastructure that's actually live? Do you have it documented in your repo at all in any way? Maybe the only thing we have is, you know, the fact that at some point there was a ticket we could find. And how do we do DR? So if, for example, we've relied on the fact that our messaging framework will provision our topics, our queues for us, if somebody gets fat-fingered, typically my experience is there's some kind of cost optimization exercise where someone decides, well, I don't think anyone's actually using that queue. I don't see any traffic on it. And it's just a queue that gets occasionally fired but has an important message on it. Someone fat-fingers it out of existence. How do I recreate it? How do I know what recreates that particular thing? Do I just redeploy all the apps? So once you reach beyond the scale of I can just talk to individuals, you're going to have some mechanism to solve all these problems. And essentially what you have to think about is discovery. How do you find and understand all the asynchronous APIs that live in your estate? Governance. How do you ensure that you have some definition of the schemas? How do you ensure that the schemas can be evolved in a useful way? And provisioning. How do we go from some kind of code that we have that uses messaging to actually ensuring the infrastructure exists for it in the first place? And that is what effectively, why we say at scale, you're going to start needing to think about all these ideas. All right, so you're going to have an understanding of how do you do discovery, governance, and provisioning, and that's what we'll try and tell you today. How do you find the async APIs in your estate? So how do I find a producer a message? Let's say basically there is a message, I want to find out who produces it, I want to talk to them about it, perhaps I need some additional information added to it, perhaps I want to make sure that my use case is okay. Do I just go and search GitHub repos? I mean, I've done that, right? You just go and find your enterprise GitHub or whatever for your organization, type in the name of the message, and just see if I can figure out which repo it comes from. And maybe that repo tells me what the team is that belongs to it. Do I post a plaintive message in Slack? Does anyone know who owns the restaurant changed message? Right? I've seen all those kind of strategies work. None of them are really that successful, right? Do I go and look through the wiki and search our wiki, which, as we all know, like all enterprise wikis, hasn't been updated in the last 18 months, and most of the information on there, while someone had a really fantastic resolve when they was originally built to create something of value, no one actually cares about anymore. Similarly, if I'm a producer of a message, what happens if I say, oh, I'm going to have to make a change to this message? You know, it turns out that naively, when we were a small startup of 12, we decided that it would be a really good idea to use integer for the ID for our orders. And now we've been successful, it turns out that there are only so many integers and we're running out of them. Maybe we should turn it into a string, but that's going to require me to communicate to everyone who's currently using the message. Do I ask in Slack? Do I search the repos? How am I going to find who all the consumers are of restaurant hours changed? Right? So it's a tricky one. So we might imagine, well, potentially maybe there's some prior art here. And certainly if we think about the world of HTTP, most of us, I'm sure, well, who's familiar with Swagger stroke OpenAPI? Because you can't see, that's basically most of the room, right? And so effectively, we already have ways of doing this for HTTP-style endpoints. And there we effectively already tend to document, right, the address, the binding, and the contract, the URI, the protocol HTTP, and the schema of the contract, what flows over it. So we need something similar for asynchronous APIs, right? We need to basically say, we need to document the channel, the topic, the protocol, the message schema, right? So we've solved it for synchronous APIs. Why can't we use the same solution for async? And that's where AsyncAPI comes in. So AsyncAPI is a Linux Foundation project. It's effectively next door to OpenAPI in their cluster. Effectively, AsyncAPI, which is modeled originally on OpenAPI, does the same job. It basically says, here is some JSON or YAML that describes my endpoint, which I use for messaging. Right. So, an AsyncAPI document consists of the following elements. A server. So the server tells you basically what the broker is reasonably. Why is it a server, not broker? Because it also supports basically things like WebSockets as a model. So server is a more generic name, but it tells you how do I connect to the server and what is the protocol it uses. It tells you the channel, says what is the name destination to which messages are produced or can be consumed from. It tells you about the message, tells you what the data, the payload, and the metadata is. It tells you what application this is. So AsyncAPI is application-centric. In other words, typically an AsyncAPI document defines your application and defines what how it interacts with channels and brokers. So the servers and channels and messages you can define centrally, like a component list, and then you can pull them in as just a reference. Typically, a document says my application sends or receives from a given channel. the operation, what you're actually doing to the channel, send or receive, just discussed, and the bindings. So you may want to define your async API as something more than just, here is logically what I do. You may want to say, I do this, but I do this over Kafka. And here actually is some important information, for example, the number of partitions on the topic that I have. Okay. We'll come back to that a little bit later when we talk about provisioning. Okay. So this is the structure. Any one of you who basically dealt with an open API document, this structure would look remarkably familiar, I suspect. At the top level, we have the kind of async API object. Root object just says this is an async API document. We have the info object with the usual collection of metadata. Yes, internally you can declare that, you know, what is the license you've used for your particular schema document. A server's object, so basically that is the connection details for the server, just discussed, the broker. The channels object, so what channels basically are in use. An operation object, which basically then says what are you doing on these channels. Components is essentially that we can take any one of these ideas and put them in, if you like, a file which just contains a lot of them, which could be a separate file to our application file, which we can just use $ref to actually reference and pull in information from. And it's essentially locate things like channel definitions, messages, and brokers that are shared across many applications. And then tags, in case we have some tagging system we want to use to add additional information. We can also, by the way, as well as using tags, you can create custom bindings. So custom bindings are another way internally of adding additional metadata that you might need to do things like provisioning. Okay. So it supports the following schema formats out of the box. Effectively, it assumes that you are going to use JSON schema. That is basically widely supported, it's human readable, very easy to use. It also, you can use Avro. So Avro is obviously big in the Kafka ecosystem and essentially is pretty useful as soon as you start to deal with things like iceberg tables, Flink, and all that kind of ecosystem that extends beyond just Kafka itself. And then effectively things like protobuf are also supported as a mechanism that you can use. The other thing that you can use here, which is supported, or that doesn't require direct support, is CloudEvents. So CloudEvents is a standard for our metadata. So there are a number of required attributes for CloudEvents, which essentially is every event needs to have a unique identifier, it needs to have a source to say who created it, it needs to have a type, which says what is the name of this event, so what's the human readable name, and which version of that have we got. And it has a spec version, that's the CloudEvent spec version itself. And that is effectively the required attributes. A number of optional attributes, this isn't all of them, but we'll highlight some. So the data content type, which is incredibly useful, it tells you in the metadata how to read the body contents, which if you're writing a generic framework, for example, like I do on Brighter, it's incredibly valuable to be able to essentially have something which says, okay, I can look at that and determine how to deserialize, serialize your message. The subject, which you can use to qualify the source. Sometimes it isn't enough to know just as producing application. You need to qualify the source a little bit and the time that it was sent. There are also extensions for things like claim check pattern, etc., and those kind of things which you can dig into. By its name, one of the implications is that CloudEvents is intended for events. Now, just slight aside quickly, if you get into messaging, we tend to distinguish technically between messaging and eventing, right? So messaging is things going over queues. So queues tend to have locking, and you can read past lock items, process them out of order, and you acknowledge and they're deleted. And eventing tends to go over streams. So you can think of streams as a file with an offset that you're reading into. So Kafka is typically historically been a stream, or that's just got support for queues or messaging, and typically AMQP was originally messaging, although it now weirdly also supports streams. So most brokers now support both approaches, but historically it was often that they would support one or the other. CloudEvents specifically says it targets events, not messaging, and that is because its standard doesn't have a standard for some things that may become important in messaging context, like a reply to header field. That aside, nearly everybody I know uses CloudEvents as the standard, whether they're doing messaging or eventing, because it is useful. It just lacks some standards around things that you might standardize in messaging, like reply to. And it's CNCF, CloudEvents. So how does CloudEvents help you for discovery? So obviously the inspection at runtime, all right? You can effectively look and see in the headers what is the source and event type as they're flowing through the system, so you can actually look and say, okay, who sent this? What is the name of the message that I'm receiving? How can I try and identify it by looking it up? It's often used for routing. If you have a type of the message, you can actually use that to determine at runtime how you handle that particular, what pipeline you're going to flow that to. Particularly useful for people that like to put multiple event types on a single topic, because they need ordering between different events representing different states of change to an upstream resource, like an entity or aggregate. And it provides self-describing events. In other words, basically, it carries enough to identify it without anybody else concerned. CloudEvents have two types of binding, binary and structured. The most important thing to remember is that CloudEvents, binary and structured, have nothing to do with being binary or structured. It's a bit like the joke about the Holy Roman Empire. The Holy Roman Empire was not holy, it was not Roman, it was not an empire. So what do they actually mean here? So binary just means the underlying protocol supports headers natively. And structured means I'm not going to use native support. If there is any in the body of the message, I will write both the header and the payload in a kind of envelope format, right? And there is a JSON standard for doing that, a JSON CloudEvent standard. So originally, the purpose of this was mainly that not all brokers out there had support for headers. Most now do. But it's also useful in contexts where the number of headers given to you is limited. So for example, if you deal with the world of AWS and you're dealing with messages on SQS, then you're going to be limited to 10 header items, 10 message attributes. And they can get filled up pretty quickly. And if you want to start adding cloud events on top of whatever ones you may need locally, like for example, a tenancy identifier, then you're going to run out of attributes pretty fast. So in that case, most people, for example, operating in AWS and SQS will tend to use a structured message format so they can reserve those message attributes for things they need to use, for example, for filtering on SNS, and keep the CloudEvents metadata in the actual body. All right. So let's imagine I've gone away and I've built all these AsyncAPI documents. I've written a whole load of them, and they've got JSON schema for my messages, and I've got basic CloudEvents for my headers. What am I going to do with these to aid discovery? Because really all I've just created for you is a pile of documents. How do you make that tractable? So the good news is that there are a number of tools that would deal with documents written in AsyncAPI for you. Event Catalog is one of them. So Event Catalog, if you load your events into Event Catalog, it supports reading documents that are written in AsyncAPI, and it will give you a visualization to represent what your structure looks like. It can interpret effectively across your various documents, and you'll be able to actually understand the integration points of your system. Marmot's another open source product which does a very similar thing. Again, you just feed it some open API and Marmot will begin to basically give you some kind of visualization of how your actual flow looks in reality. I haven't got it up here, but Apicurio is also another one which will do something very similar. Apicurio has this slight advantage that you can also basically put your open API in there, so you can kind of create this universal tool for handling endpoints and schema registry, etc. There's a newest kid on the block, which is xRegistry. xRegistry is designed to really be distributed systems registry. It's just one of the things it will do is let you basically store messaging. And it Comes, if you like, as a standard with various implementations, and so you can effectively create servers that support the xRegistry protocol, but also talk protocols like OpenAPI and etc. We'll return to that a little bit when we get to schema. All right, so AsyncAPI, CloudEvents, and registry, all of those give you ways of creating documents that describe your endpoints. And when you describe your endpoints, you can put them in some kind of catalog, which eases the burden of discovery and also visualizing your system. Okay. So typically, when we think about two things, so restaurant management, restaurant availability, so if I change the hours, my availability changes, we think about them as being coupled. If you like, in DDD terms, these are two bounded contexts, and there's some kind of coupling. Often, in order to prevent us in restaurant availability, depending on all of the types that live within restaurant management, we write something called an open host service to you and I, basically an API, which says we're going to do some kind of translation between the internal domain event structure and the external structure. So that effectively creates basically a document that says, by having an external contract, which is not our internal domain model, I'm free to change my implementation details without breaking my downstream consumers. This is effectively coupling, but it is essentially necessary coupling. Because in order to collaborate with others, we must exchange something. And data is effectively the weakest form of coupling that we have. So the contract makes it necessary coupling for supplier and customer. In other words, we say, we agree we will not keep breaking this contract. It is long-lived. So if a contract is long-lived, what kind of guarantees can we make about it? So we can guarantee backward compatibility. That says that a new consumer can read old data. So in other words, we upgrade the consumer for support for additional fields that may be coming in the future. It should be able to read messages created on the prior version. Forwards compatible, which says if I produce a new message, an old consumer should be able to ignore the additional fields and still read it. Full compatibility, we go both ways, right? And no compatibility, and I'm probably going to be extremely unpopular in the enterprise very shortly. All right. You can think about it this way, all right? Generally speaking, you can add optional fields to a message without breaking the contract. If you want to remove something, what you effectively have to do is deprecate it and then remove after everybody has finally stopped using it. If you want to rename something, that's effectively a remove and an add. So you deprecate something, you add a new field, and you say when everyone's on the new field, not the old one, then I can get rid of the old one. And you could change the type, but that's almost always a breaking change. So in other words, that means effectively a new message. Okay. At scale, you can't rely on human beings to keep schemas compatible. They just won't do it. We have a whole load of PI incidents every year, which are caused by somebody failing to do that. So typically, the problem is producers just don't know about some of their consumers. Often we see this problem when, for example, data is picking up messages and using them to put into BI stores, and that the team just don't even think about their existence when they start changing something, right? And schema, typically, if it does exist, may well be, in an AsyncAPI document at best that isn't effectively being read or enforced anywhere. And tools like Pact exist, but in the messaging world, they are intrusive in terms of basically the way that they force you to write your app, and are not generally as helpful as they are in HTTP. So the answer really typically is to use a schema registry. So a schema registry effectively says, we're going to tell you what the schema of any message we produce is. And when you produce that message, what we'll do is effectively enforce that the message ought to conform to that schema. Now, you could choose to warn with the schema registry. You can choose to say, oh, I'm just going to warn you that effectively that's actually a bad message. But typically, you can also enforce. So you prevent the schema producer from actually sending the message. Because typically, it's a mistake to have deployed it. And quite often, you want to pick it up in a QA environment, et cetera, right? You can also, in theory, do some checks basically during your CI pipeline to check that effectively that's not going to happen to you, right? And consumers, in theory, can also basically check on the schema in order to basically say, okay, if I'm going to deserialize effectively that message, I only want it to be in a given format. I may have a slide in this later, I can't remember. But typically with consumers, there's a bit of a trade-off. You can use something called Postel's Law, which basically says, I don't actually want to check the schema. If I can interpret it, it's all good, right? In other words, it may not conform to the schema it's supposed to be, but essentially if I can read it, ignore fields I don't need, etc., then I'm all good with being able to process it. So Postel's Law says, be strict in what you send, be liberal in what you accept. You can't really do that if your consumer is, for example, say, populating something like an iceberg table, all right? So there are circumstances where you generally do have to do enforcement. So, given you've got AsyncAPI, generally, typically what you want to do is actually try and automate this process, right? Take your AsyncAPI, extract its schemas, validate the compatibility. So what is the compatibility model you say you're offering, forwards, backwards, or whatever, register in the schema registry, and then basically deploy, right? So you can typically effectively use both documents to automate the production basically of your schema and register them. Okay. Yeah, we've done that. Okay. So you need to standardize your schema format across the platform, review schemas as part of your API review process, integrate into CI your ability to essentially register your schema and ensure that anything basically continues to conform to your rules on forwards and backwards compatibility. And generally enforce runtime for producers unless you want to break things like your data mesh downstream. Okay, provisioning. So, how can you provision your infrastructure? So manual provisioning effectively says do it via tickets. Who does ticket ops still for Kafka topics and things like that? Nobody? You just don't need to be here then. The other way basically, the problem with it basically is typically configuration drift, all right? It turns out that over time, people don't really know what is the configuration required. The only way to figure that out would be to do some kind of retroactive look through all those tickets to find out what was the sum of everything that we actually added together in order to get to the current infrastructure. So it's almost useless for DR, right? If Scattered Spider attacks you and takes you down and you need to rebuild your entire platform in a new environment, you're going to be struggling because you don't know what it looks like. Often, doing this manually tends to run into problems with name conflicts, right? And often the ways around that tend to vary by team. They have their own naming standards. No one's really documented how we should do this. And so we get into all sorts of problems with collisions. And there's nothing that really says what is supposed to exist. Okay. DR's redeployment, right. So, what you want to do is have a specification that tells you what is my messaging infrastructure look like, all right? So before, basically, you were using ticket ops. After, you want to use a specification. Define what should exist, generate from the spec, validate automatically, and the spec becomes a source of truth. Okay. So, AsyncAPI provides a generator framework. So what happens is essentially, it's basically built with React, and you can essentially take a specification, you can write a generator template, and then effectively parse an AsyncAPI specification and do something with it. Very typically, what you do is you transform it into something else. Now, originally, this was kind of written so that you could create fancy HTML documentation from your AsyncAPI documentation, but the way a lot of folks have started to use it is to essentially parse your AsyncAPI to figure out what you need to provision. This is why bindings are useful, because the bindings let you add information to your AsyncAPI document, which gives you the requirements that you need to understand how should I provision this Kafka topic. All right. So, a typical model looks a bit like this. Take your AsyncAPI spec. extract basically the binding information that you need in order to say, I need this Kafka topic with these particular properties, provision those topics or queues, and effectively once you have a document which tells you what essentially this should look like, look for drift. So the way we do this, I've got a slide later, but we'll see how clear it is. We do this with Pulumi. We effectively take your AsyncAPI spec. We extract all the information from that to give us effectively a picture of what our runtime messaging infrastructure should look like. We use Pulumi to provision that, and effectively then we can check for drift. Okay. Yeah, you can also generate documents. Right, that's cool. All right. So, should we spec-driven, code generate, auto registration, and DR then becomes tractable. All right. So, how do we do it? So we have a tool we call MEX. There are about 2,000 message schemas in there at the minute, about 600 services, and about 625 what we call auto-gen pipelines, which are basically pipelines for generating infrastructure for a message schema. And this is kind of how it works. So we take basically the AsyncAPI YAML spec, we shove it through something lovingly called Mextrapolator, which is basically a C# tool, because it turns out that Lego were kings of building libraries for doing AsyncAPI. Who would know? That turns it basically, we take all of the specs that we currently have and we combine them together. Because don't forget, effectively, you've got servers, channels, messages, which are kind of centralized resources, and then applications which are using them. So we parse all that in Mextrapolator and we figure out effectively a graph of what we need. That's then stored as a JSON artifact. That JSON artifact then is loaded by MEX. It's a separate Go program which effectively reads that artifact and then deploys it to various stacks that we need. Once it's been deployed, we get a notification it's been deployed, and we then effectively take that same artifact and we write it to Marmot so people can effectively go and have a look at what our messaging infrastructure is doing and have an easier path towards discovery. Schemas are basically extracted from the AsyncAPI template. We effectively build basically a model based in the schema, then our Pulumi code effectively registers that in the schema, and we, as part of that process, tell you what compatibility level we are offering. The only thing that can write to the schema registry is MEX, and effectively it has a process of toggling writes on or off by getting a token, so that essentially it prevents developers going into the schema registry and manipulating events by hand. And then we basically do broker-side, we do validation, and we reject messages that don't conform to a schema. Right. So, Marmot then provides a data catalog for us, which lets us do basically to see basically the services, Kafka topics, SNS topics, and SQS queues that we use. We at the minute basically use SQS for queues and Kafka for events. Whether we will change that decision when Kafka queues rolls out more solidly across more providers than just Java remains to be seen. And it gives us then lineage relationships basically across the producer to messages to how they flow through the system. And engineers can effectively use that to do discovery. All right, let's wrap up. So, when we think about managing messaging, there are three things that we need to care about. We need to care about discovery. How do I find basically the endpoints that are relevant to whatever I'm trying to do? We need to think about governance. How do I ensure that when I have essentially messages, that contract that I'm describing in terms of my schema is honored, and any kind of transition follows reasonable rules so I won't break people? And how do I provision infrastructure in a way that is a repeatable process? Even better, something that just automatically detects drift and copes with it. A few things are still hard. Consumer-driven contracts is not very satisfying. Schema registry is probably our best bet today. Things like pact are just really intrusive, and I don't particularly like them. There's no real system for inputs and outputs. So in other words, the problem is that AsyncAPI will tell you this application receives these messages, this application produces these messages, it won't tell you that the application produced this message because it received this message. There is no way of saying what flow looks like. There is an attempt to solve flow for OpenAPI called a RATSO, so it's possible they'll extend that to AsyncAPI. This doesn't do everything, right? The other thing you need on top of this is telemetry to tell you what's happening actually in your system at runtime. You can go and look up. I look for the one at NDC Oslo last year. I did a separate talk with Martin Thwaites from Honeycomb about how you do that. And adoption, yeah, you have to get the teams to do it, right? And convergence, xRegistry is not really caught up with AsyncAPI. All right. There's your takeaways. I will leave you on that slide. And that is that. Thank you very much.